So in this video, I'm going to talk about my final architecture modification proposal. I call it ResNetPose. It's based on ResNet34 architecture. I'm just writing on top of ResNet34. I'm basically using so I'm doing sort of transfer learning in here to come up with the 25 channel outputs. That is the 9 channels for belief maps and 16 channels for affinity maps. So this is the ResNet34 architecture. Let me zoom out. So this is the ResNet34 architecture. You can see the residual connections in here easily. You can see the residual connections. This is the ResNet34 architecture. I collected this image from internet. So and in here I try to calculate the 25 channel outputs in here. This is cascade 1, cascade 2, cascade 3, 2, 3, 4, 5, and 6. I'm trying to utilize the pre-trained weights of ResNet and I'm experimenting with whether I can come up with a neural network structure which calculates the 25 outputs that I need, 25 channel output that I need. So I will go over the ResNet architecture and where I start working. I take samples from there. So this is the layer 1 in the original architecture. This is the layer 1. This is called layer 1 in pattern implementation. This is called layer 2. Layer 2. This light red one. This is called layer 3. And finally in here, this is called layer 4. At the end of layer 1 in here, I end up with image features of size W by 4, H by 4, zoom up in here, by 64. That's what the image features look like in here. At the end of layer 2 in here, it looks like, or I would say at the start of and the end of this, it looks like W by 8, H by 8, by 128. The image features look like this. And the end of layer 3 in here, I end up with W by 16, H by 16, by 256. Note that the image size or the feature map size has already gone 2 times below than what I need. I need image features of size W by 8, H by 8. I will come back to that later. Next, at the end of this chain in layer 4, I end up with W by 32, H by 32, by 512 channels. Again, this is almost 4 times downsampled sizes that I need. I need W by 8, H by 8 size. Now, let's look at how I do my map calculation. So in here, I will just get rid of this. I've already written it in here. Same as this one, I've already written it in here. So in here, with the blue writing, I am representing the image features that I'm getting in here. From this here, I sample the image features, or I use those image features. Again, they are of size W by 16, H by 16, by 256. So you see, so now I do my cascade 1. They work with image features of W by 16 by H by 16, and the cascade 1 then comes up with, actually I could have drawn this better anyway. So the cascade 1 comes up with image feature maps, 25 feature maps. As you can see in here, it comes out through this way, each of size W by 16, H by 16 size. Then this predicted belief maps on cascade or maps, I would say maps, belief maps and affinity maps. These 25 maps are then passed on to cascade 2 in this direction, and also just like before, the cascade 2 also gets the image features of channel 256 size and spatial width and height of W by 16, H by 16. Just like before, it calculates 25 feature maps and then it passes those 25 maps to Cascade 3. Cascade 3 again gets the image features in here from here and then comes up with its own 25 version of 25 leaf maps. Now let's complete the chain, then I will come back to these parts. Let's just complete the cascade system. So now in here, in this part, I take features from here which are of size W by 32, H by 32 by 512. They are passed on to each of these three cascades. So I've basically divided the chain into two sections. The first section of the first three cascades work with image features that are taken from the output of layer 3, and the rest of the cascade 4, 5 and 6 work with the image features calculated or taken from the output of layer 4. So it takes as input these red features in here, each of size W by 32, H by 32 by 512. And it also, as Cascade 4 also has to take into consideration the previous predictions by the network. So I am actually sending these features in here, but before that I'm doing a downsampling by 2. Why? Because if you look at the feature size in here, image feature size in here, they are the spatial width and height is W by 32, H by 32, whereas the belief maps calculated in this part in here is W by 16, H by 16, but I need W by 32, H by 32, so I need to downsample it by 2. Now in here in this part I downsample it by 2. As a result, now these 25 maps are converted, the spatial size is downsampled by 2, and I end up with W by 32, H by 32 by 25. Now they can be used for the cascade system in Cascade 4, and now I send them in here in this direction, and Cascade 4 comes up with its own 25 feature maps. Again, their width and height would be W by 32, H by 32, and there will be 25 of them. Now these 25 maps are passed on to Cascade 5. Cascade 5 again receives the original input image features, comes up with its own 25 feature maps. Then Cascade 6 does the same thing. It takes as input the previous detections from the Cascade 5 and the input image features, and it comes up with the final 25 feature maps. Now I'm going to talk about what are these things. Let's start out from Cascade 1, 2 and 3. Remember that my ground truth belief maps are of size W by 8, H by 8 size, but the produced belief maps or the produced maps are of size W by 16 by H by 16. So the spatial size is 2 times smaller than what I need. That's why I need to do upsampling. In the network implementation, I just implement a bilinear upsampler by bilinear interpolation to do the upsampling. I could have used convolutional encoder-decoder structure, but that I didn't know. I experimented with that. I did not end up with anything good. So for saving time, I just implemented. This time for presentation, I implemented only upsampling using bilinear interpolation convolution, interpolation upsampling. So I just upsample these images W by 16 by H by 16 to W by 8 by H by 8. As a result, now I have the spatial width and height same as my ground truth, and again I maintain the 25 channel output. Same thing goes for each of these. But in here, the produced maps are of size W by 32, H by 32. So I need to upsample them by 4 times, not 2. And in here I do that upsampling by 4, upsampling by 4, upsampling by 4. As a result, I end up with W by 8, H by 8 size, and the map number, channel number still remains 25. Now I can do my loss calculation. Just like before, I will take these outputs. Let's say this is my loss block. I'll take these outputs in here. Same as these things. I will send them to the loss block. I will compare them with their ground truth, and I will come up with the back propagation gradient flow, backwards gradient flow, and I will pass them on in these directions, just like before, so that I can train these models. So this is the proposed architecture, which I call ResNetPose. The objective of this ResNetPose architecture was that for faster gradient convergence. Oh, I forgot one thing. So inside this Cascade 2, I am not using regular just conflare, then ReLU, then batch normalization. I'm not using that. Rather, I'm using same structure as this. So if you look at in here, these are called in ResNet architecture. These parts, these individual cells, are called basic blocks. They have these residual connections. Let me use red actually. They have these residual connections, which makes the learning of hyperparameters or this or makes the gradient flow much better than regular without a network without these residual connections. So these basic blocks already have inside them implemented these residual connections, the identity connections. So inside these cascades, instead of using regular convolutional layer architecture, I use these residual blocks, 3 of them inside each of these cascades. So each of them inside will look something like this: one block, a second block, a third block. This one connecting in here, and this one connecting in here. They will all have residual connections. Now, why I did that? That is because of better gradient flow. Because if you remember what I said before, the gradient is coming down from this direction, right? The gradient is coming down from this direction. The gradient also coming down from this direction, right? Now, once I have the gradient flow in here, I will have a better gradient flow due to the residual connections in here, the identity connections in here. As a result, my hypothesis was that these convolution layers will be easier to train due to better gradient flow. And if you look at the entire architecture now, this entire thing has, from end to end, has other than just these blocks, from end to end, these have identity connections, because the loss is coming down from here, then it gets identity connection through this way, then again this way, then again this way, then the loss goes to in here, then the loss again gets an identity connection from here to here, then again here to here, here to here, then again here to here. As a result, from starting out from even cascade 6, it will have a very good gradient flow. The gradient flow will be direct, and that's my hypothesis, is that as the network is very long, like some in the original dope 2 architecture, architecture, it has 92 layers. So if I use residual blocks as well as batch normalization in here, then probably I will get a much better gradient flow and my convergence will be faster. So that is something also I wanted to experiment with in this architecture, and wanted to get a practical idea of how things work out. Then, so this is my ResNet pose architecture and experimentation architecture, and I'm going to present the implementation details and results in the Jupyter notebook in the project. Thank you.